So my name is Michael, Michael Vertolli, and I'm going to sort of lead the discussion here. I'm a PhD candidate at Carleton. I work on deep learning, specifically with generative adversarial networks. But I did want to start, I actually didn't prep this, but I did want to actually start based on previous conversations. Who actually tried to read the paper, if you will admit? That's okay. You can also not admit, that doesn't matter. And who actually found it difficult? I just want to gauge. It's not a problem if you found it difficult. Yeah, okay. Anybody find it super easy? No, okay, well, interesting reference point. All right, so what I want to do is, in terms of this quick outline, is I'm going to try to contextualize with the first half of the talk what exactly is going on in this paper and why you should care. Okay, so it's going to start a bit with the motivation, some prototypical examples, go through a bunch of models, talk about some very recent developments that lead kind of nicely into the work in the paper. And then in the second half of the talk, I actually want to talk about the two models that are presented in the paper and some of the million experiments that they present. And then we'll close with some wrap-up stuff that ties things back together. Okay, so the underlying motivation or the underlying context that we're working in here is latent variable models. Okay? And the basic idea of latent variable models is that we're trying to approximate very complicated distributions, data distributions, indirectly. Right? And one of the main ways that they do this is by modeling that, approximating that distribution by conditioning on some prior distribution, which they call either latent variables, a code, or sometimes even an embedding. And then we always consider things in terms of these divergence criteria. You're going to hear me say the word divergence a lot. Part of the reason why I'm using this word instead of words like loss functional or stuff like this is because I want to point to some more sort of general properties related to how we actually design these models. Now, one of the challenges with using these models is that most real-world distributions are ugly. Now, what does that mean? Well, in essence, what it means is it means that whatever assumptions we're going to make when we're building our models, we're kind of automatically going to have them violated by the underlying distributions, right? They're just never going to conform exactly to whatever the expectations are that we have. Now, that can mean lots of things. That can mean the underlying distribution isn't actually Euclidean, so using distance metrics or pseudo-distance metrics that are Euclidean doesn't actually make sense. It can mean that they're discontinuous at certain points. It can mean they're non-differentiable at certain points. It can mean all kinds of things. It doesn't really matter. All that really matters is that at the end of the day, our assumptions that we bake into how we design these models often result in particular types of patterns of modeling errors in the distribution, okay? Or in our error distribution. So, just to get some basic stuff out of the way, we're working in an image domain. Okay, so we're looking at X is always going to represent some real image from some data set. The data set, in this case, our data distribution is going to be P data. Okay. We're looking at Z is going to be noise vectors sampled from some prior or some embedding distribution. We can think of it as that way. We're going to have a generator network called G, which samples from the decoding distribution, which is this, P given P given Z. And effectively what we're just doing is we're going to give that generator network the noise variable, or that noise vector, and it's going to output some sample in the data space. And what we want to minimize is the divergence, well, which is always going to be this D of our data distribution between this data distribution and the decoding network. Sorry, my mouth is very dry. Okay. So that's the basic task. Now,
Sorry, can you go back?
Yeah.
Why is it that not P of X? Why is it P of X given Z?
Because we're actually, this is an approximation of P of X, right? So as you'll see in a second, we're actually looking at the distribution that exists as a consequence of encoding based on conditionally on the prior. Does that make sense? Yes.
If your input to the generator is Z,
yes,
doesn't that make the output deterministic?
It depends.
Okay.
It depends on the model. In some sense, it is deterministic. Right.
Okay. So P of x given z, in some cases, will be a delta function, basically.
Yes.
Okay.
Yeah. It depends on the model, right? You can add noise, as you'll see later on. More complex models will actually add stochasticity at different points in the model.
Okay. So what you're trying to minimize is the divergence between P data and P of x given z integrated over Pz. Is that right?
Yes.
Okay.
Yes. 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 So you can take the marginal. Yes.
Yeah.
Yeah.
Okay.
Yeah. Okay. Yes. Okay. So base case, VAEs or variational autoencoders, right? Is anybody familiar with variational autoencoders? A little bit, a few nods. Okay. Yes. Good. So the basic idea, we're trying to model P data indirectly in terms of this embedding distribution. We're going to represent the embedding distribution in terms of a family of Gaussians parameterized by their mean and variance. Okay, that's clear. In order to do this, we're going to include an encoding network. We're going to call that Q that samples from the this distribution, which is, you can think of kind of as the inverse of the generator. It's not actually true, but intuitively we can think of it in that way. But basically what Q is going to do is it's going to take some actual real image and give you the approximate embedding vector in our desired embedding space. Okay? Yes?
Just wondering, isn't this only true if your metric of training error is like the square of error? So the Gaussian interpretation only applies under that assumption. Do you have any other reconstruction error metric that's not really valid?
Yeah. So yes. 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 There is a certain truth to that. Yes. The key point here is that we're introducing a new divergence, right? We also want to compare now not just how does our generator actually output samples relative to our data distribution, but we also want to compare how does our embedding network, right, or our encoding network, Q, actually produce samples in our embedding space as well, relative to the original data space. So there's two separate things that are being monitored here. And what that allows us to do, in the case of variational autoencoders at least, is it allows us to simplify how we're going to minimize that equation, and we basically end up with what you can think of as a form of regularized autoencoder, right? So this is your loss function, your standard autoencoder loss function, and this divergence here is with the data distribution, or with the embedding distribution, my apologies, is a regularization term. Okay.
So
yes.
So you're trying to minimize the loss function in the embedding space between like some, I guess, the Gaussian of Pz and the Q of Z given X.
Yes.
Okay.
So it's basically this guy right here. So Kullback-Leibler divergence, we want to make sure that our means and covariances are similar to an isotropic Gaussian, right? And that actually is why you're right. Technically, that only works in a Euclidean space, but if we control for this, if we add this regularization term, you can actually sort of force the embedding to fall in a Gaussian space regardless, right? Roughly. Does that make sense? Do you see what this regularization term is doing? You could just think of it as saying, we want to make sure that these things output by the encoder actually are similar to this isotropic Gaussian. It's similar to a Gaussian. So we're constraining the embedding space to actually match the expected distribution. That's what this is actually talking about, right? Hopefully this isn't actually going to be confusing, but I've tried to keep the talk a little bit light on equations. This literature can be extremely dense in terms of these equations, but I don't know if it's actually useful. I do have some of the actual loss functions and stuff at the end if you do want to see them, but I think you can kind of get the basic idea. So anyway, this is our encoding distribution Q. They use a slightly different notation, so they're calling their decoder F. I called it G because in the paper that we're actually talking about, they call it G, and in GANs they generally call it G. But anyway, so we're taking a real sample from the data distribution, we're piping it through the encoder to produce these embeddings. We're going to regularize those embeddings, but for now we don't need to worry about that. We add stochasticity. This stochasticity just basically smooths the embedding space. That's all it's really doing. Pipe that into the decoder or our generator network in the case using the notation that I talked about previously, and then we take the squared Euclidean distance between the output of this after passing through the embedding and the original value. Does that make sense? This is basically just an autoencoder, and we're regularizing the embedding space. Yes?
It might just be semantics, but why are we calling that regularization?
You can think of it as a form of regularization. In the literature, this is just how they kind of talk about it. I think the reason why is that if you go back to regularized autoencoders, there are some similarities where they'll actually do things like inject noise into the embedding space and stuff like that. What's the concern?
Practically, all you're doing there is that you're enforcing the distribution that is coming out of that to be similar to a normal, I guess you call it isotropic distribution, right?
Yeah, that is exactly what it's doing. Yes.
Okay.
So if the distribution sharply diverges and actually bears no resemblance to a Gaussian distribution, that's going to severely adversely impact on performance, right?
Well, because you're kind of doing this, remember it's being done with something like stochastic gradient descent or something like that, if your model is it's going to try to keep it near that. If it rapidly shoots off into space, you're going to get noise. Yeah. So yes. Yes. Yes.
Just wondering if introducing a random perturbation is the canonical way of training it. I was under the impression that most variational method.
You're talking about this?
Yeah, use some kind of log derivative trick.
Sorry, which? Use a which?
Log derivative trick. Basically, they try to they try to apply the gradient on the mean and the variations.
Yes. So yeah, the reparameterization trick is what you're saying. Yeah.
Yeah.
No, you're not saying that.
Log derivative trick.
Okay.
That's the same thing. It's the same.
Yeah.
If there is a name for log
derivative, log derivative would be those regularization terms exactly, like the square norm, like the 2 norm of the, yeah, that's exactly what it is.
Oh,
yeah. So this is just a
My point is, does that eliminate the need to introduce random perturbation?
Here, in practice, no. Theoretically, sort of. So if you think about it formally, it kind of makes sense, but the fact of the matter is that to the extent that our data actually isn't Gaussian, adding smoothing, this is just a smoothing term, adding a smoothing term actually does in fact help the model at the end of the day. So, yes?
Is that like a smoothing term, or is it like the innovations process basically? Like if you're talking like stochastic calculus, you can just put a white beam filter on any stochastic process, and you're going to get white noise, which is called the innovations process of that original stochastic. So it's like the actual remainder stochasticity in your space, like an image. If it comes from a distribution, has a certain randomness to
yes,
it.
Yes.
So it's not a smoothing parameter. It basically allows you to select or sample from the distribution. It's more fundamental than that.
What you're saying is it allows you to have a one-to-many mapping, right?
Yeah.
Right. So yes, but if you think about what that actually means, in some sense, the underlying manifold is being smoothed.
So
it's not not in any sense. Like if you don't have that C, there's you can't dispense with the C because then
it will be a one-to-one mapping.
It wouldn't be a generative model. You can't generate stuff.
Well, it still would be a generative model. It just would be deterministic, going back to what you were saying before, right? Okay, so yes, you are correct. It is very much the case that this is this allows you to have a one-to-many mapping. Absolutely true. In many contexts, it's also used to kind of smooth the distribution, but we'll just put that aside for now.
If you look at it from the perspective of the derivatives, you can actually compute the derivatives during background, and I think that's why people call it smooth, because if it's non-smooth, if it's non-smooth surface, you can't really compute.
So it makes it differentiable, but it's not a smoothing parameter.
Well, people use these terms.
Yeah, it's just how they talk about it in the literature. But you are correct.
Exactly.
At the end of the day, you are correct.
Yeah.
So what I heard about the reparameterization trick when I was reading the paper, So the idea was, oh, we have autoencoders, but instead of now the embedding being something fixed, we want to draw from a statistical distribution. And to simulate the statistical distribution, they create those means and these variances, right? But if you would just simply draw from it, you cannot do any backpropagation on it.
Yeah, right.
So what they do, they add these noises and just sum up, multiply basically the standard deviation plus the mean. And this way they get a fixed value for each data point. And then they can backpropagate through these fixed states.
Yeah, exactly.
So tell me that the training becomes bad because the variation is too low?
Yes.
That's really weird.
Well, yeah. It's a very deep point, but it's partly just because the underlying data distributions that we're looking at are insanely complicated, right? Like, truly try to imagine describing to a computer how to incrementally piece together somebody's face, right? Like, and the set of all possible faces, human faces, right? And so an extremely complicated distribution. And so really what you're saying on some level is that you can't possibly have enough variation, right? In some small data set. You would probably need millions or billions of images, which
So effectively, the additional variation prevents overfitting by kind of relaxing the right. That makes sense.
It's like data augmentation almost.
Almost, but in this weird embedding space, right? Okay, the downside of variational autoencoders, which everybody in the literature knows, this is actually kind of like model bashing almost, is that the output is blurry, right? And that kind of makes sense. You're embedding distribution, or you're trying to make it look like a bunch of Gaussians, and well, maybe on some level, this is what Gaussians look like, right? So I believe these are actual output from a VE from this paper, and I believe it's ImageNet or something that they're generating based on. I don't actually know what these things are. They do look like images. I think we can give it that, but it's not clear. A lot of the high frequency information has been lost.
Is a lot of that due to commonly using mean squared error as the
Yes.
loss function?
So yes, partially. You're doing the jumping ahead thing.
I don't know what's next.
It's okay. Yes. So one of the intuitions, it's hard to say for sure, right? There are a lot of different papers that are talking about why we're getting these errors, right? But one of the intuitions is that this mean square error, the underlying data distribution just isn't Euclidean, right? So that doesn't actually make sense. But anyway, the core intuition, again, that we want to point to is that we want to have a larger possible space of embeddings or embedding distributions that we actually want to represent it. And one way that we can do that, one more slide. There are a lot of different explanations for why that's the case. One of the ones that I actually like a lot is by Mester et al. And what they show here, this is actually the model output in the latent space. So this here is in terms of the mean and variance of the encoding network. Sorry. And what they're showing here is actually the heat map is showing you where the highest variation is in the output values, okay, in the output images. All right. And what they also note is that you tend to get the blurriest images where that variance is the highest. Now their intuition is basically that when the variational autoencoder is mapping the real life data points to the embedding space, basically what's happening is it's mapping multiple data points to a single embedding value, right? So in PZ, we're getting multiple different images collapsing to a single embedding value when in actual fact they should be being kept apart. So my geometric sort of interpretation of this is saying on some level you could imagine that this red shape, the heat map, is actually describing some higher order, more complex topology in the underlying data's manifold, all right? And what's happening is that when we project that higher order information using the divergence functions like Euclidean, like squared error, onto this latent space, we're losing that information. It's we're seeing collapses across categories, basically, all right? So that's the kind of thing that I want towards. Yes.
Does that mean that the dark blue areas are sharper?
They're sharper, but they're also simpler, right? There's a lot, like when you generate something in this area of the latent space, you more or less always get a one that is vertical.
Oh, okay, yeah, this is MNIST. So.
Yes, it's MNIST. It's a little bit easier than faces. Okay, so although this is historically inaccurate, pedagogically it's useful. So one way we can generalize variational autoencoders is in terms of what are called adversarial autoencoders. And what adversarial autoencoders do is they allow us to map to an arbitrary embedding distribution. How do they do that? Well, they do that in terms of a discriminator network, which unfortunately I'm going to call D. Don't confuse it with the D with the tail. That computes the probability that some Z value, some embedding vector or noise vector, did in fact come from the embedding distribution. All right? So in terms of the variational autoencoder, we can think of this as an adversarial form of regularization. Now, for those of you who have seen the GAN literature, this is going to look weird because I'm minimizing relative to Q. Q's in here too, and the expectations are actually reversed, right? For those of you who are familiar. If nobody's familiar, then that point was completely meaningless, and all that matters here is that the adversarial loss can be thought of as a minimax two-player game, all right? Where basically the discriminator is trying to keep apart the synthetic values, the values generated from the sample, from the actual real data points which we sample from analytically, right? So what the discriminator wants to do is it basically wants to maximize, right, that distinction and preserve that binomial's distribution effectively. And what the generator wants to do is it wants to do the opposite. It wants to minimize the number of its samples that the discriminator is identifying as fake. Okay? Really, this just boils down to cross entropy. It's actually quite easy, even though this looks super, super confusing. Now, how does that actually relate to what we were talking about before? Okay, so you have an autoencoder. We're still computing the squared error here, right? But in the regularization step, we're now breaking the regularization step into two parts. First, we're going to optimize this discriminator, and what it's going to try and do is it's going to get synthetic samples from the desired distribution, and it's going to get output from our encoding network. And what it wants to do is it wants to be able to keep apart those two distributions effectively. So during that part of the regularization step, we actually backprop this, trying to keep that using cross entropy. And then during the second part of the regularization step, we're only going to regularize Q, and we're going to regularize it in terms of the actual error that I was talking about before. Now, in practice, theoretically, we talk about this as a minimization. But in practice, that's actually not as stable as doing a maximization of the sort of reverse. So instead of actually minimizing the number of samples that it gets wrong, we actually want to maximize the number of samples that it gets right. That's kind of a technical nuance, but it is worth keeping in mind that whenever you see this equation, it's actually only an approximation of what's done in practice. Is that clear? Roughly? No. Yes. Questions? Do we see what's happening here? We're trying to, same thing as the variational autoencoder. We want our embedding distribution to match some random arbitrary PZ, right? And what we're doing is we're creating this sort of adversarial tension between the encoding network and the decoding, and the discriminator, my apologies, and the discriminator, such that this one wants to figure out which of these are not actually from the real sample, and this one wants to make sure that these actually are from the proper distribution. Does that at least what I said make sense? I'm seeing a nod. I'm seeing a couple nods. Hopefully that makes a little bit
So
of sense.
how is it, I think the question is, how is it not capturing the min-max function?
Oh no, it's a
How's it
max
different?
max. It's a max max. It is a minimax in a formal sense, but it's a max max. Because in actual practice, we don't minimize 1 minus dz.
I see.
Okay, we actually maximize
So
the opposite.
that's what you meant when you said it doesn't exactly reflect this equation.
Yes, that's what I meant.
Fair.
Yes.
I think that was.
So just wondering, the QZ in that diagram, the law, next slide.
Yeah.
That QZ,
Where
we
did- yeah.
we don't impose a form on that. The only way we can calculate that is through the marginalizing that conditional. So
Yes.
So we don't really, because you know, the point that is kind of confusing to me is that you were talking all about, oh yeah, like we want to make sure that we are transforming the input space into a Gaussian space. Whereas
For phase.
here, yeah, like if the network, like it's only how the network is designed or the hypothesis space that
Well, it's
determines
this.
what QZ would be.
It's this part. It's this. It's whatever you're using as a point of reference. Does that make
so
sense?
PZ is designed to actually resemble QZ, or?
No. PZ is picked, and we force QZ to conform. So
Or
for example, here, PZ is a mixture of Gaussians.
Okay, yeah.
Here, PZ is a Swiss roll. It actually doesn't matter what PZ we pick, hence it's arbitrary. But what we're going to do is we're going to force our encoder to embed our data distribution such that it maps onto whatever distribution it is that we want to make.
But isn't it like aren't we training a discriminator? So we want to make QZ as distinct from PZ as possible, or?
Only relative to this gradient.
Okay.
For this gradient, we actually want to make QZ as close to 1, right, which is this data distribution, as possible.
First.
Question?
Sorry.
Yeah?
Is that perturbation gone?
Yes, so we don't add, we're actually not using, so you're thinking of this,
Yeah.
right? We're not doing this sort of piece necessarily at all. You could, but yeah, in this case, you don't need to have perturbation here necessarily.
And second, that Gaussian perturbation seems to be, kind of more reasonable, and a better way should be replace it with some, some upper effect, like lens effect, or to simulate, raindrop on top of it, something like that.
Sorry, I didn't quite get what the question was.
The perturbation
Yes.
doesn't have to be Gaussian.
Oh, like for here, or before?
For the old one, yeah, the VAE.
It doesn't have to be Gaussian. I think that the perturbation that you pick would have an impact on how the gradients, how you handle the gradients, but I would have to think on it more deeply. I don't actually use phase. I'm just actually using it for a pedagogical reason.
You're talking about the VAE, right?
Yeah.
Using Gaussian simplifies the KL divergence.
Yeah.
So that's
Yeah.
what that's you mentioned, the regularization trick.
Yeah, but when you calculate, but when you want to calculate the loss, when you want to calculate the gradient, having the Gaussian makes it tractable.
Oh.
So what happens is you usually compute elbow.
Yes.
And for elbow you need it to be Gaussian. Oh, well, for it to be tractable.
For it to be tractable, Gaussian is
Yeah.
one of those things.
So one of the main reasons why the original Bayes used Gaussians was to simplify the entire process, right? Again, if you look at the chronology, Bayes did come out before GANs. Yes.
So I'm still totally confused by this slide. So if QZ is like the QZ given X, so if like I'm thinking of it as like neural networks. So we initialize with some random release. So QZ given X, I don't know.
Would be, it's effectively noise. This would be just random activations.
So, like, what is the training regime for this? Like, are we going to start with a randomly initialized Q network and then train with the outputs from that, or we just a priori like?
No, it's just you can use random weights. Yep.
Okay.
And random initialization. It's outputting something that at first. Remember, but this is also random weights, so the discriminator also sucks in the beginning.
Yeah,
right?
at the beginning, but like we like first propagate gradients back from the discriminator.
So we first minimize this, or maximize this, and then after we do that, we then it's actually a two-step optimization, and you usually even will have like a separate like if you're using Atom or something like that, you'll actually have a separate calculation for each network.
Okay.
That
So
makes
once
sense.
you optimize the bottom, like the
But you're not optimizing this fully. For one iteration, we'll pass some batch through. We propagate the gradient for this network. Well, technically, we propagate the gradient across the whole thing first in an autoencoder way. This is just an autoencoder. Then the regularization step, which is asterisk.
Okay.
Does that make sense? You got it?
So it's a series of like alternating steps.
Yes.
Like, okay.
Yes. Sorry if that wasn't clear. Yes, it's not happening all
Can
at
you
once.
continue your thought? I didn't get it.
Oh, what was my thought?
So
Okay. So first we do the autoencoder loss. Fine. Step one. Now, separate step. We optimize the discriminator, okay, relative to how well is it keeping these things apart, right? So every one of these values has a 1. The distribution is effectively, this is a 1. These are zeros. How well is the discriminator actually mapping to that distribution? Fine. Now we're looking at just the encoding network, right? Just Q. Now what we want this one to do is actually make it so that the discriminator thinks all of the values coming out of here are just 1, right? That's what we're trying to maximize. We want it to be 1. We want it to think that it's these values, effectively, right? And so we're going to propagate the extent to which it's not 1. The gradients go through here, but we're not training this network. And then we're actually just training here. Does that make sense? So it's 3 separate steps. Yes? It's a good thing to go through these things because it only gets weirder.
Just so then you know, you have half an hour.
Oh, geez. Okay, so let's move quicker. Generative adversarial networks. So what's the key step here is we can in fact map arbitrary distributions. So why would we focus on the embedding then? Remember, the original motivation is we're actually trying to map to P data, right? We're trying to actually map our data distribution. So what generative adversarial networks do, historically this is wrong, but we'll just ignore that fact, is they just approximate dx, the divergence from the data distribution directly. All right, so what does that mean? Well, it means that our discriminator is not going to compute on the embedding space, it's going to compute on the output space, on the sample space, right? So we're actually going to compute the probability that x came from P data, right? This is a weird statement. I'm going to actually not cover it right now because it's a little bit nuanced and I don't have time. But this is now the sort of standard adversarial loss. For those of you who are familiar with the GAN literature, we're minimizing relative to G, which is the generator network, and notice that the expectations have flipped, which is what I was actually saying before, right? So the expectation here is relative to P data, or PD, and this expectation is relative to the prior. But in every other way, it's exactly the same. There should actually, I messed up things here. There should actually be real samples here as well, but very, very simple. We have no Q network anymore because we don't care. We're just going to sample directly from whatever it is. Usually it's Gaussian or uniform, some distribution. We're going to pipe it through the generator. It's going to output some sample, and there's going to be a discriminator sitting on top that is going to try and keep apart real data from samples. The whole point of actually going through all those steps was just to make this easier, which hopefully it did. Make the earlier parts hard. Is that clear? We all know, have some sense of what a GAN is doing. Right? Good. And lo and behold, that blurriness has gone. These images still suck, but we now are actually able to capture high frequency data. All right? And this is actual real output. Again, I think it's ImageNet, but I'm not sure. Okay, last few steps before we get to the paper. I'm going to go over this really quick, so we're going to stay on questions. I'll cover them as we go into the actual models. Conditional GANs. Similar to regular GANs, but now we're going to fuse our noise embedding values with some conditional embedding, right? That's all. Pretty easy. LapGAN, I wanted to cover this in a bit more detail because it actually is very informative of what StackGAN is doing. We don't have a lot of time, so the intuition is that we're going to now actually have multiple generator discriminator pairs in a Laplacian pyramid. Okay, so these are effectively different resolutions you could think of, or different frequency resolutions. You're capturing different frequency data, right? And what the generator is doing now is it's going to use this data almost as kind of like a conditional. This is our noise prior, and what we're actually going to output is the difference, the information that was lost, or the residual information that one would have expected to find in the higher resolution image. All right? And why I wanted to show this is that this notion of capturing things across multiple scales is very, very critical to what StackGAN is doing. All right? And the second thing I wanted to point out, because this is a distinction with the second version of StackGAN, is that we've traded our sort of general notion of divergence from our data distribution with a bunch of local divergences. We actually no longer know, in some sense, what the true our actual model divergence is from the entire output data. We just don't know what that is. All we know, all that we're actually capturing here is, well, is the model able to capture this information? Is the model able to capture this information? And so on. And that's going to change with StackGAN version 2. Yes?
Is the difference between different layers here, like the second one is just the downsample version of the first one?
You're actually passing a Gaussian filter over them of different frequencies, if that makes sense. So you're smoothing out different amounts of information.
Okay.
I don't actually remember if they do make the images themselves smaller. I don't think so, but the key information, from what I remember, is that the frequency information that you're capturing as you move across these is changing.
I see. So they're not literally smaller. Just the
I
frequency
don't.
content is smaller.
I don't think so. They are representing it as that. So it may be that as the information collapses, it shrinks. I can't remember, unfortunately. Yeah. It's more the sort of theoretical piece that I wanted to capture. So a couple other things here. So these two are models that did text-to-image synthesis, which kind of maps us into our domain. The key detail is that we're basically building conditional GANs, but our conditioning distribution are text embeddings. They add this sort of interpolation detail, which I'm not going to cover. And then GAN actually does something very similar to the other model, but they have this very strange notion of spatialized embeddings. We're not going to worry too much about that either. I'll cover StackGAN version 1 in a minute. And progressive GAN just came out last year. It was done by NVIDIA. The key point there is that you would train a layer to produce, you would train a network to actually produce a certain resolution image. Then you would stop, you would add more layers and train that whole network again to produce a higher resolution image again, right? So again, what I want to keep sort of highlighting here is that there's something special about this multi-scalar, multi-distribution capturing notion that a lot of these things are trying to get at. With the text-to-image precursors, they're really just comparison models.
Progressive GAN would have one distribution.
Yes.
For
Well, depends on how you think about it, right? Because technically, that first chunk of layers was trained across multiple sets of discriminators, right? At each of the resolutions.
Right.
So in a weird way, it does actually have a representation of the full thing at the end, but the earlier layers went through more iterations of that, if that makes sense. So there's a slightly more complicated underlying thing going on there.
Yeah, I see what you're saying. On one level, you do at the end have one distribution.
Which the LabGAN did not have.
But you also have the 4x4
Right.
distribution before you fade in the next.
Yes, exactly.
Okay.
Two clarification questions, very quick. If you go
Yes.
back to the previous slide.
Yes.
Do you happen to know what GAN stand for?
Oh.
Okay.
What and where, I think, network? Something what and where?
Okay, that's fair. And the other one is GAN, interpolation.
Class.
Class?
Interpolation class, yeah. And class just means we're using a text embedding, and interpolation, they did something interesting in the training step, but we'll
I assume they use that for adding caption to videos or things like that, or generating images from captions?
yes.
Okay.
Yeah. Which is what StackGAN does.
Oh, okay.
Yeah, text to image synthesis. So what does StackGAN do? Right? We've gone through all of this sort of story now. StackGAN version 1 breaks our generation task into 3 tasks. Right? First, we're going to conditionally generate small images from text embeddings. Right? Second, we're going to conditionally generate big images using those small images, and again, the text embeddings. And third, we're going to use this weird Veil-like augmentation to actually, and this is their words, smooth out the text embedding. All right? So, beautiful diagram, by the way. Beautiful, beautiful, beautiful diagram. So just going over this quickly, top is stage 1, bottom is stage 2. So we train this network fully, both the generator and discriminator and this little bit. First, then once we're done, we stop training this and we train the bottom one on using the output of this as input to the next stage. Okay? We have these special text embeddings, which are coming from a pre-trained network that I'm just not going to talk about. I do have an extra slide if you want to know anything about it, but it's not really important. They have a pre-trained network. The network, one detail that is critical is that the embeddings were trained or created using image-text pairings. So it's non-arbitrary to the domain of application, right? This conditioning augmentation step should look very familiar. We have some fully connected, we have an embedding, we have some prior, right? We have some fully connected network in here, and it's going to output the mean and the variance, and it's going to add a little bit of noise, fuse that together, and then that's going to be our actual embedding that we pipe into our generator. So that's super familiar, right? This is a VE right here, effectively. But it's a weird VE because our prior is a embedding distribution. Now the way they don't talk about it in that way, what they talk about it as is we want to introduce additional noise. We want to literally smooth out, that's their words, the underlying distribution, right? Because otherwise the mapping is too coarse as they move through. Okay. We concatenate that with the noise vector, upsample, we get this 64 pixel by 64 pixel image. The discriminator now downsamples that into a 512 by 4 by 4. We don't use this, stop touching the screen. We don't use this. We go back to the original embedding, have a fully connected network that compresses that vector, and then replicate it spatially across this other embedding-like thing. We're not going to talk about that as an embedding, but in some weird way, you can think of it that way. And then our probability distribution, our sigmoids, are computed on top of that. Got it? Kind of makes sense? See why we did all that work before?
You want 28 parts, that I didn't get.
Sorry?
You want 28 parts.
Oh, this piece?
Yeah.
Yeah, so we took these big embeddings, we passed it through a fully connected network to make them smaller, and we replicated them spatially across the entire thing. Cool? We're just trying to make it so that the amount of information that's coming from the embedding is sort of, not exactly the same, but roughly proportional.
So in the downsampling step, you use also information from the real image? It looks like it.
Here?
Yes.
Remember, it's trying to keep, the discriminator is trying to keep these two apart. These two did. So yes, the real images, the information from the real image is being
Oh,
passed
this is
to it.
stage 1 discriminator.
This is the stage 1 discriminator. Yes, exactly. So discriminator, generator, weird conditioning augmentation network. This piece gets trained along with the generator in tandem. This piece gets trained as like the other step of the two-step process. Is that clear?
Yeah, just when you say unsample, you're generating an image from the latent representation. Is that what you mean?
Here?
Unsampling it, right?
Upsample means that it's scaling up. Yeah. Okay, stage 1. Yeah.
And the text description is attached to that real image.
Yes, in the data set, which we'll touch on in a second. Stage 2.
So the embedding you get from the discriminator stage 1, you feed into the stage 2 generator. So it's kind of
This arrow is confusing. So what actually is what this is actually saying is we take this base embedding from the pre-trained network and it goes everywhere. Right? So they just take this embedding, it goes into a fully connected network that is unique to this, goes into a VE unique to this one, goes into a fully connected network unique to this one, goes into a VE unique to the stage 2 generator, goes into another fully connected network unique to the stage 2 discriminator. So literally it goes everywhere.
Very confusing arrow.
Yeah. That's why I'm here. So, similar to what we did here in terms of spatial replication, because we're now working with images, we have to downsample back to here, and we're going to replicate that, that embedding again. Now, this is actually another VE, and there's some argument that they make that you want to have another separate parameterization basically going on here, because in stage 2, you're hoping that the network captures aspects of the embedding of the language distribution that are unique to generating higher frequency information or larger images. In other words, that are unique to capturing the information that isn't currently contained in this small image. If that makes sense. We're going to pipe that through here. We eventually get the image. The discriminator effectively is trained exactly the same, but it's just trained on this. It's just trained on the 256 by 256. Yes?
Sorry, maybe I didn't get. Why do you concatenate not discriminator? Why do you concatenate after the offset, but not before?
Why do we not concatenate with the image?
Okay, I see. So, okay, never mind. So
there's a few reasons. One, I mean, it would be tricky to concatenate with the image, but
it's the image, okay.
yeah, because these are images that are being input. But there's other reasons. They do interesting things here in the training routine. One of the things they'll do is they'll make the discriminator actually learn to identify both, I think it's real images, real text, real images, random other text. So you just randomly interpolate out into the embedding space, or into this embedding space. And then fake images, fake text. So you can actually do some interesting things in the way you're training the discriminator by being able to control that information. If that makes sense. Very, very, very complicated. Okay, what does StackGAN version 2 do? All right, the key insight about all of this is we're trying to capture higher order relationships across sections of the network, across scales in the network, basically. Right? How are we going to do that? Well, like with LapGAN, we're going to have multiple generator discriminator pairs. Unlike LapGAN, we're going to have this interesting sort of almost like progressive GAN notion of the entire divergence, which is really just the sum of the divergences across each of those scales. I'll explain that a bit in the next slide. We're going to condition on multiple levels, so we don't, that actually doesn't make sense right now, but I'll show you in a sec. And we're going to add another form of regularization called color consistency. And basically what color consistency does is it tries to make sure that the mean and variance of each of these images is roughly the same. Okay, what is going on here? All right, we still have that conditioning augmentation, although it's not being shown. So we still got this, but this is so complicated they decided that it was wise not to include it. We're gonna upsample, all right, and create what you can think of as an intermediary embedding, all right? We're gonna take that intermediary embedding, pipe it through just a small convolution block, and produce some kind of quote-unquote image, right, in a lower resolution. We're just gonna ignore that for now. Following on along with the path, we're gonna take that conditioning variable and embed it back in, again, at the higher resolution. So we join it back up, propagate it spatially like we did in the other network, send it through a bunch of residual layers, upsample. We now have a slightly different embedding that's supposed to capture new information, higher, like information about the larger image. Again, we repeat that process, have a unique generator and discriminator. Finally, we do that one last time, and we call it a day. Okay, so why did I say that weird line here about we have sort of a local and a global notion of divergence? Well, when they calculate the gradient for this network, they're looking across all three of these generators, the error or like the difference in the distributions, the adversarial loss, you could say, or whatever, across all three of these distributions. So the gradient for this, the error gradient in here, is going to include information that it's getting from this, as well as its contribution to this layer, information that it's getting from this, and as well as its contribution to this layer, information it's getting to this. And similarly, you're going to have the same thing happen here. So this one's going to get information, like with progressive GAN, from this one, and so on. So unlike in LapGAN, we now actually have this sort of higher order notion of divergence across the entire data distribution. But that divergence is made in terms of these sub-divergences or local divergences, if that makes sense. Kind of clear?
Mike, well, there is a question for me, a big one. just say, how is it different again? So I think the best way for you to address the question is go through this once more, because I don't get the difference between this one and the previous one. So the previous one you had, if you go like a couple of slides back, you have this modular approach. Each one has its local term and a global term that will link you from the global loss. That was sort of easy to understand.
Yes, but this is two-stage. We trained this fully, stopped, trained this one.
One low resolution, the other high resolution.
Yes.
This is just
all of the training is happening at the same time.
Right.
There's no stage one.
Right. And what are the trapezoidal things?
These things, JCUs.
Yeah.
So JCUs, it's a little bit convoluted, but basically what's happening is they've now duplicated their loss term or their divergence term here. Okay? And the unconditional loss is more or less exactly the same thing as this, but we, instead of concatenating conditional vectors in here, we add noise. Okay, we add some prior distribution. And then the conditional loss is exactly the same thing, but with the conditioning distribution. And they found, as I'll show in the experiments, that this actually does this additional conditional information.
What is it, conditional?
The text embeddings, with that weird Vey smoothing thing.
So where do we measure loss? Do we measure loss once after 256, or do we measure it 3 times?
So,
steps?
So in what sense? What kind of loss are we talking about?
Explicitly, I guess.
So the loss. So there is a loss here, right? And for the discriminator, when we're training this discriminator at this level, D0, it's only here. Is that clear? So all it cares about is how well it can identify these from real and fake.
Yeah.
Same thing here. Same thing here. Now, the actual generator loss, in a weird way, is actually up here, even though, again, we're looking at the cross entropy here, here, and here, but we sum it, and then we propagate the error based on the final step. So you need the information to have gone through all of the information or all of those intermediary generators. You sum it,
so,
right?
So the local loss over there would propagate to other. So if you go back, yeah?
Yes.
So like the first pass.
Yes.
The first network.
This
it
part.
has a loss. Its loss could propagate to the next network. Because you're saying that
the error in here will propagate here, but we don't know if that error is actually going to be represented. I mean, on some sense it will, but we don't know if in some sense the insight is that the aspects of the error that are being captured here are different, although related, to the aspects of the error that are being captured here. That's the point of this multi-scalar sort of thing.
So I guess yes and no question. Do you have a global loss term which includes the local losses as well?
Yes.
Okay. Yeah.
Does that kind of make sense? Yes.
The next item. So for the GCU discriminator, do you input like also the embedding again into the conditional loss, or is that like I'm just indicating that the embedding is being
Yeah. No, it is. It is. It's like this. Yeah. It's extremely dense. Yes.
I'm curious, why do you think the residual layer is before the outside? Because intuitively, the residual layer
These?
defaults to pass through, and you kind of want the image to first put the small image enlarge a small image and then add several layers that defaults to pass through.
So I think what you're saying is that on some level you want the sort of global structure or shapes to be represented in here. You want to pass that information in here and then add additional finer grained details as you go there. Is that what you're trying to say?
No, well, it's the other way around. You first enlarge the picture. You first
the upsampling step?
Upscale the picture, and then you fine tune all the details.
So yes, we upsample, in a sense, we upsample here, but are you saying intuitively you would want to upsample the 256?
I'm talking about the second and the third.
Right, the second and the third, you're doing residual networks first and then upsampling.
Yeah, I think.
So you're saying why do we do that?
Yeah, I think it should be upsampling and then residual.
Why is that?
Well, upsampling is like, because residual defaults to pass-through. So basically, we don't train it. It's just like,
Yeah, so-
enlarging the image without adding more details.
Yeah.
And then you gradually make it to let the residual add.
So your intuition is actually correct, but your alignment with where we're actually evaluating things is slightly off. So your intuition is basically saying we would upsample, then pass residual information after we upsample. Where I think the issue is that we don't actually want to evaluate the generators after we've done that residualization, because I guess on some level the intuition is that whatever we're residuating here, right, which again, there actually is more information because we've added in the conditioning vector. But whatever information we're residuating here, we're actually, the pitch is that that's critical for this step, right? So your intuition is actually correct. We upscale and then we residuate. It's just that when we make our evaluation, we make our evaluation before we residuate. Does that make sense? So the intuition that is you would upsample first and then residuate, that's correct. And that is actually what's happening here. The only thing that's confusing is that we're kind of taking intermediary samples along the way.
It's
So
like,
is it fair to say that then in the second layer, which is green, blue, pink,
Yep.
essentially you have your joining network and then your residual network, and then you just do upsampling exactly as he's saying in order to pass it on to the next network
Yes.
to add more details. So your intuition is exactly, I think, what the network is. So you do upsampling,
Yeah.
add detail, upsampling, add detail, upsampling.
Yes.
yeah, but is the criteria supposed to compare to the discriminators criteria should be comparing the image with detail with the original image.
Yeah. Well, at minimum, just because there's still a few more slides. They did a lot of experiments. At minimum, it's something that we could evaluate, right? Like you could. I don't think they do not. But you could actually try sticking it at the end and see what happens. At minimum, right? And it may be better, and that would be actually a very interesting finding. Cool. Bunch of text. Don't worry about it too much. There's a few data sets that we use. So birds, flowers, slightly more complex. El-Sun, which is bedrooms and churches, dogs and cats. Unconditional basically just means that there's no text associated with this. Bunch of evaluations. I would love to go into them. They're super interesting. Inception score, Fréchet distance. They actually use human raters as well. They use multiscalar structural similarity index or similarity metric to compare things, and they output the latent space with the TSNE and press it into a two-dimensional space and look at the output as well. So lots of stuff. Don't have a lot of time to go over it. The only thing I do want to touch on is that both these inception score and Fréchet distance, what they do is they'll actually take the images, pass them through a pre-trained inception network, and look at the embeddings some higher layer and compare the embeddings across either within the distribution or across the distribution and the real distribution. Yes?
All right, a quick one.
Yes.
The second set of data sets, the unconditional ones, does that mean that there's no labels attached to it? But there's no text embeddings that they feed in?
There's no text embeddings.
Yeah.
Yes, that's all unconditional.
Is that why we do the humans?
Sorry?
Is that why we do the human evaluation?
Oh, that's a complicated question. No, the reason why they do the human evaluation is because there's the StackGAN v1 paper is actually embedded inside the StackGAN version 2 paper. So the human rater evaluation happened much earlier in time, and there weren't as many metrics back then. A lot of this stuff is new. In the field, it's still not, the jury's still out on what the best way is to evaluate models.
Yeah, that's also one thing I wanted to say. I mean, raters are the only reliable thing you have right? Inception score. I wouldn't really count much on that. Not for services. Yeah.
The scathing review of these other papers, but you're not wrong. But you're not wrong. Okay, results, and I'm going to show you actual images.
Before you talk about the results, do you talk about the task?
The task?
Yeah. So like, what's the task that you're showing?
We're generating images.
Out of text. Out of text. Because
In
you
the
have a few
conditional,
different data sets.
in the conditional, out of text. In the unconditional, not out of text. It's just generating images. That was the question.
How do you evaluate? Like
Exactly.
Okay.
That was what that question was.
So people would say it's a good image, it's a bad image. Like this
That's
image
sort of with the human
makes
rater
sense.
situation.
And do you have categories for these images, like bedroom, church, whatever? And people say it's a church, or people just say this image actually visually makes sense.
So the human raters I don't think are for this. I think the human raters, because it's for V1, is for this. So what the question that they actually asked was, given this text, is this a good image or something like that? Or rank these images in terms of their quality.
I just took a peek on their topic while I came here. I think they evaluate on two things. One is, does this look real? And
Right.
second is, does this match the caption?
Yes, there you go. So many things. Okay, StackGAN version 1 outperforms everything on everything except StackGAN version 2. And I'll show you, you can be a human rater for a moment. StackGAN version 2 outperforms V1, version 1, in terms of FID and the ratings. Wait, now I'm starting to think that there might have been human ratings for version 2. Anyway, don't worry about it. But when we're comparing these things, StackGAN version 1 and 2, the differences tend to be small. At least quantitatively, the differences tend to be small. Okay, we get to actually look at something. So, GAN, int class, gone, StackGAN version 1, StackGAN version 2. Here is some text. So, I really like this one actually, because I like that image. This bird is red and brown in color with a stubby beak. Fine? So, you can see right away high frequency information. Remember that? That was sort of the original motivator. Not a lot of high frequency information. Still a lot better than this, but I mean, you're getting some little details, but this is also blown up really big. Gone, a little bit better. You can see a little bit of gradation there. There's actually quite a bit of high frequency information here in these really weird trees that I don't think I've ever seen in my life. But okay, as we go to StackGAN version 1, a lot more high frequency information is being included. We're getting flecking in the wings, fine. Some interesting color here, very nuanced beaks and stuff like that. And then StackGAN version 2, if you actually just showed me this, I'd actually think that was a bird, right? So this is not a bird. These aren't real birds. This is output by the model. And if you look, there is a crazy amount of high detail in here. And the fact that it's actually capturing the stick 2, which it wasn't trained on, remember? It's like there's no stick component to this data set. It just happened to figure out that, well, there's a lot of sticks underneath birds. Oh, yeah, yes. Trees and birds are correlated. Now let's look at these data sets. Again, just, this is, I can't even explain to you, this is insane. Like, the quality here is insane. Like, that it's able to get this very, very high detail in the flecking, and so on. The intricate detail in here, and so on. And again, really, notice, when you look across all of these, I mean, okay, that's a little weird. I don't know if I'd eat that. But you're not getting any of this weird banding, right?
I think you can say that's weird because you can actually tell. It's like for humans we have a better eye. Like for birds, I can't really tell apart if it's either male, female. Like,
real bird, fake bird.
Yeah.
I mean, like I'm
For
looking at
humans,
the person in the snow. I can tell it's not a group from this distance. It pretty convincingly looks like a skier waiting to get on the chairlift. I'm sure at your distance.
Yes,
you know,
as
there's
I'm,
something wrong with it. but
yes,
from
its
my
head.
ear-
It looks terrifying, actually.
Yeah.
It looks like one of those like Slenderman or something. Or maybe that's a bit more Slenderman. Anyway, so The other sort of interesting thing which I really liked about their analysis is they actually look at where does the model fail. And the TSNE thing, which I was doing first, this is the TSNE of the latent space, and you can see right away mode collapse is happening here. So within the embedding space, this region is not actually being represented. If we had more time, I would talk a little bit more about that. In StackGAN version 2, you just don't have that. There's no mode collapse. And modal collapse is like an open problem in the GAN literature. That's just like it's not solved. So this is a big deal. This is what that means.
So what does it mean to modal collapse?
It means this. It means some region of the embedding space just produces an identical image. So it's kind of the underlying distribution is collapsed to a mode.
Okay.
To a high.
That was my next question.
Do they do this for every data set?
What is who's they?
The authors, I guess.
This is new. Now, like if we go,
So
I'm not going to go way back, but
does it show no mode collapse for every data set that they tested their model on?
they don't show all of. If what you're saying is, do they create these images for each one of the data sets?
Yeah.
I think they did. They don't show it in the thing
Okay.
Or in the paper. In the thing. I'm getting tired, guys. They don't show it in the paper, but they report that the V2, the second version, does not suffer at all. In fact, it actually never has even moderate to severe. Now this is super qualitative, but their argument is that these issues on the bottom is StackGAN V2. These are never actually severe. They don't always call it mode collapse, but like severe errors. There's a relationship with mode collapse, but right. I have difficulty evaluating crappy images.
I've heard people describe mode collapse as when the discriminator and the generator stop competing. Is
Yes.
that accurate, or is that?
Yeah. So So convergence occurs at Nash equilibrium, right? And what that requires is that you more or less have a balance between how well the discriminator and the generator are doing throughout the training routine. If at any point one of them starts to do much better than the other, you just the model will shoot off into weird space. This is more subtle than that because, as you can see, when you get like severe mode collapse, the whole representation space would be one image. So this is a bit more subtle. I can't say confidently that this is a competition issue in this case.
How far through the layers is this representation? So I assume it's embeddings.
Good question. Can I answer that? I can't answer that. You got me. Yeah.
No, just for clarification, because I was trying to understand the pixel.
I would suspect. Can I say that? Usually you would do it here. Okay? But the reason why I can't answer that is because these points are interesting, you could argue that it could have actually been done at another point. I still suspect you would do it here.
So just to clarify, so you run the TSNE on the input keys, or like the conditioning variable or whatever, like, is that what you meant? Because that was like a two-dimensional space with a bunch of image patches.
Yeah.
So
Effectively what you do is you would take these noise vectors, right? And depending on how you want to do it, you could actually take the noise vectors that actually correspond with real images, or you could just take the entire noise space, you collapse it down into 2 dimensions. Yep, exactly. And then you use the mapping between those two things in order to plot. So you kind of go back from the 2-dimensional space to the higher dimensional space, and from the higher dimensional space you pipe it through to see what the image would be that corresponds to
Because
that thing.
from the receptive fields, you can always go back to which image it was. But my question was, which distribution are we talking about?
Yeah, I suspect it's this one.
Yeah, no, just want to.
when
Oh.
the TSNE were to like capture the topological structure of
Yeah.
the thing, supposedly it wouldn't really matter.
Oh.
High pure
You know what? Actually, maybe that's what I do. And then let me double check. I can get back to you on that one. It may be that they actually ran it on the output images, right? And then they just mapped it in that space as well. Because you could also just process TSNE on the output images by the model. Because if they did it based on purely the embedding, I think you would get, like, how would it capture that? Like, that seems odd, right? So anyway, let me rephrase that. I think I actually got that wrong. I think the TSNE is actually done on the output images. In my work, I actually do it on the embeddings. Yes?
Well, I think both of these pictures of the change looks non-gradual, so I'm wondering if the network spent a lot of effort memorizing the training data set. Or
Yes, so they have actual comparisons showing like nearest neighbors and stuff like that to check for memorization. And they show that at least, I believe, with StackGAN version 1, that isn't what's happening. Okay? I don't think they reported in StackGAN version 2. The problem is I didn't include that image because there was already however many 30 slides.
36.
Yeah, but there are images reported in the original paper that talk about that specifically. And they argue, I mean, it's not perfect, but they argue that you're not having just strict memorization. It's complicated though, because they're often comparing images using like mean square error, and we know that images aren't actually similar in the context of mean square error. So their approximation of what the nearest neighbors are is already weird, right? You know what I mean? These questions are very, very hard questions.
Yeah, but
Oh, sorry, go ahead.
sorry, I mean, well, if they can change only two elements of the vector and see the image gradually change from one
Right.
to another instead of snapping,
Yes.
that's also another evidence.
Yes, so, and they do have, there's like embedding space interpolations are also shown in the, I may get to that. Do I show? No, I'm mostly showing the comparisons.
Is it the case that if you train a network long enough, it will hop, that region may hop to another mode?
I've seen that happen in my own research
Yeah.
with GANs, that you can get mode shifts, but the distributions are often complicated enough that once it's, I've even actually seen, you know, it's not always true. I've even actually seen it collapse to a mode and somehow find its way out again. So all kinds of weird behavior can happen depending on what exactly the distribution is, how exactly, like the GAN literature is nightmarish. You could train it 1-to-1, you can train it 1-to-3, you can train it 1-to-5, like what is happening anymore, right? So I'm saving you a lot of the story. Okay, qualitatively they say StackGAN version 2 outperforms all of these other GANs, and these WGAN is considered pretty state-of-the-art. LSGAN is also quite competitive. StackGAN version 1 is competitive. But what I really want to draw your attention to is the detail down here. Like the fact that it's capturing lights and curtains, which have transparency, is insanely impressive. Insanely, insanely, insanely impressive. Okay? The last piece, we're going to ignore this, the last piece is they show that when you chop out different pieces of the underlying stack, like modifications that they made to StackGAN version 2, interesting things happen, right? So there's something very critical about the way we've structured the network in general, right? So this is just StackGAN version 2. This one has 3 generators at the top level instead of 1 at each of the scales. And as you can see, kind of goes to whatever that is, paint maybe. This one only has 1 generator at the top level. And this one has generators that all generate images at 256 by 256. So they're not scaling up the resolution as we go along. And you can see something is very interesting that's happening here that as you break down, so just having more generators isn't enough. Just having a higher level generator with all the conditioning is not enough. And changing the scale of the underlying image that's being represented is actually somehow critical. The embedding distribution, no JCU, means that they're not using conditional on it. And they argue that you're getting a lot less variation. I have difficulty evaluating that here on the basis of these images alone, but sure, maybe. These do seem to be better, right? Again, detail even in the wood. And then this I thought was super neat. the color consistency loss, which I didn't talk a lot about. Again, the intuition here is that you're trying to constrain across resolutions that the mean and variance in the color of the images is similar. It's sort of like this extra regularizing term. The top one is StackGAN version 2 without the regularization, and the bottom one is with it. So I honestly think that the word color consistency is a horrible term for this regularization, because it's not just color that's being fixed here. There's all kinds of interesting structural information that's going on. Like this is almost blurry. I don't know what these are, like really, really weird artsy paintings of churches maybe, whereas this is a lot more detailed.
So just as a refresher, the way you kept color consistency was make it conform to the mean and SD of the original image? Is that how?
No, not of the original images. You don't care about the original images at all. All you're trying to make sure is that at each of the resolutions, at each of the generator points, the images that are being generated have roughly similar means and variances in the color. Cool? All right, last slide. Everybody tired? I am. Discussion points. So there seems to be something critical in the dependencies that we're getting across these scales, right? Something interesting is happening there, and I mean, these slides really tell us that it's not replicated by other things that would be common sense reasons why. So it's not just extra generators. There is some special relationships, and we can see this in terms of frequency. There's a conditioning variable at different points there, and there's this kind of color consistency regularization. The other talking point that I'm super interested in is what is going on with this sort of what I'm calling compositional. It's not really compositional, but maybe aggregate divergence, right? So when we take this sum and we're getting these gradients from all of these different scales, something interesting I think is actually happening. And it gives us a much more nuanced notion of divergence. There's a really actually interesting paper about how if you don't have multiscalar information, the distributions of images is strictly discontinuous or strictly non-differentiable if you have boundaries that move around. And I have a reference at the end if you're interested in that too. So it would basically say that you could never represent an image if you don't capture across different scales, if there are boundaries. So that's a very strong claim, but it takes it from a very strong mathematical foundation. And then this last point is just really that there's a lot of interesting relationships and dependencies across a whole bunch of different embeddings. We have text embeddings. We have augmented text embeddings. We have noise priors at multiple layers in the network. There's this weird compressed space right before the discriminator performs sort of like a linear separation of the underlying distributions. And there seems to be relationships across all of these different, I'm calling them embeddings, but whatever, these different representations maybe, if that's more general, that are critical to understanding and representing the overall data space. And I'm interested in talking about that one as well.
Okay, hold on. Is this,
I'm done.
Talk? Okay, let's clap first.